In this video we're going to look at current and magnetism. So we've seen before that if we consider three charges, so I already sketched three charges here, if we subject them to an electric field, that you see indicated here, so this is the electric field vector, these three charges will move in this direction. Now we can characterize the movement of these charges with the current. And the current is defined as the total number of charge that traverses a certain surface, so I indicate a surface here, that traversed through this surface per unit of time. So the current is characterized by I, so this is the derivative of the total amount of charge, dq, over a specific time, dt. And then always a current is something that goes through a specific surface. This is important to keep in mind, so we always consider a specific surface through which a current is flowing. So if this is an electric conducting wire, it is the cross-section of the wire through which the current is flowing. Now current is indicated by ampere, so its unit is ampere. And of course we can see from this equation that 1 ampere is equal to 1 coulomb per second. And we've seen before that coulomb is the general unit of charge. Now the current always has a direction. So in this case the positive charge is flowing in this direction, and the direction of current, or the current direction, is always equal to the direction of the positive charge. So in this situation here, the current is flowing in this direction. Now, if we consider negatively charged particles, so I draw a situation here with three negatively charged particles. So similar particles. So if they are moving in an electric field in the same direction as we have here, so note that that of course means that now the electric field is pointing in a different direction. We take the current as the direction that positive charge is flowing. So in this case, the current would be directed in this direction, opposite the movement of negatively charged particles. So there is an important thing to realize with current, and that is its relation to magnetism. But let's first look again at what we have learned about charge. So if we consider a charge Q, somewhere in an environment, in space, the presence of that charge Q gives rise to an electric field E around that charge. And that electric field E gives rise to a Coulomb force. I will now put a subscript C here for Coulomb force that is present on other, that is exerted on other charges, so other charges, other Q's in the vicinity of this charge Q. So there's a force between the Coulomb force between these two particles. Now if we look at a moving charge, so we have a charge Q or multiple charges Q that are moving in a specific direction, like the situation indicated here or here. This moving charge will lead to the presence of a magnetic field, which I will indicate with B. And this magnetic field vector will give rise to a force, which we call the lorentz force, which acts on other moving charges. Yeah, so the electric field charge, the Coulomb force, always acts on charges in general, static or dynamic. A magnetic force is generated by moving charge, so a current generates a magnetic field. There's a magnetic field around a current carrying wire, but that magnetic field also acts via the lorentz force on other moving charges or other current carrying wires. Okay, so we now look at the magnetic field B, and typically we express that magnetic field in units of Tesla, so abbreviated by a T, or Tesla, where we should note that 1 Tesla is a huge magnetic field. So typically we speak in terms of micro or nano Tesla. So we've seen that this magnetic field exerts a force on moving charges, and this force is called the Lorentz force. And the magnitude of that force, the magnitude and the direction, so is given by the magnitude of the charge on which the magnetic field acts, then the velocity of that particle plus its direction, so the vector v, and then the cross product with the magnetic field vector b, so which includes the magnitude and the direction of the magnetic field. So if we look at a particle, so I depict a positively charged particle here that is moving in a specific direction here, so this is the velocity vector v, charge has magnitude q, and I consider a magnetic field that is pointing, in this case, into the screen. So I indicate this like this. So for you, it's pointing into the screen. So this is the magnetic field vector B. Here also B. Everywhere in this area, there's a magnetic field pointing into the screen. Then we can find the direction of the cross product by rotating V in the direction of B, and then if we would do that perpendicular to that direction, we can do that with our right hand, then the direction of our thumb gives us the direction of the magnetic field. So this, in this case, gives us a Lorentz force acting on the particle in the upward direction. So this is the direction of the Lorentz force that follows from the Lorentz force equation. Now, importantly, if we look at a negatively charged particle, so I'm going to draw a negatively charged particle here. Again, we give this particle a charge q, but now, of course, this q is negative. So let's indicate this with minus q, so the same magnitude as the one here, but of opposite sign. We again consider a magnetic field pointing into the screen. So this is our magnetic field. And again, the particle is moving in the same direction as we had here. And note that what we have just seen, in this case, there's a current in this direction. In this case, the current is pointing in the other direction because the current is defined as the direction of positive charge. So now again, to find the Lorentz force, we have to rotate V to B, which gives us the same direction as this one, but then the Q here is negative, so the force is actually pointing in the minus magnitude of Q times V cross product B. So the Lorentz force in this case is pointing in the downward direction. So here. So let us now finally look at what this means for this moving particle. Say this is one electron. So the electron is moving in this direction. It experiences force perpendicular to the velocity. So the cross product always gives a force perpendicular to the velocity and perpendicular to B. So the particle will start to move, and it will actually be deflected under the influence of this force. So it will experience an acceleration in this direction. So what happens is that the magnitude of the force is not changing because the force of the velocity, because the force is perpendicular, but it will change its trajectory and move in this direction. So say the particle has moved a certain distance and then it ends up here. So now the velocity is pointing in this direction, V, and still in the same magnetic field, B pointing into the screen. So now if we rotate V to B, again, the Lorentz force stays perpendicular, so will now be pointing in this direction. Again, with a minus sign, because the charge now is equal to minus E, the charge of an electron. So we see that the force is again changing the trajectory of the particle of our electron, and it will actually start moving in this direction. Now we can continue doing this. So if the particle ends up here, its velocity is pointing in the downward direction, magnetic field is still into the screen, we rotate them and we find a Lorentz force pointing in the opposite direction as the velocity was initially. And so if we keep on doing this, we see that the particle actually starts following a rotating, a circle trajectory, which is characteristic for the motion of charged particles in a magnetic field. We will see that it's important in electron microscopy. If we work with magnetic lenses, typically our electrons that we have will start to follow spiraling or circle trajectories.